Alright, welcome back. I want to now go through and do the second problem that is on that the handout that I made for you, okay? Again, whether you print it or not, that's your business, but you definitely should have it and be working your way through it and following it as we are working on this video. So this problem gives us, oh, it's not a story problem at all. It gives us some equation that looks hideous. Actually, I like this one because it is kind of a mess. And they say, find the dy dt, the derivative, how y is changing with respect to x when, at the time when x is equal to -2 and y is equal to -1, and given that the change in x with respect to time is equal to -4. I wish that this was the kind of thing where I could have Desmos up next to me and you could see what's going on, but I bet that's a really exciting and interesting equation. And what you would find is, okay, so at this location right here, we know that the rate of change of x is such and such. What is the rate of change of y? Alright, how are we going to actually do that? Well, part of what I like about this equation is that it gets a little messy and we have to demonstrate lots of ideas. We're going to take the derivative of both sides of this equation with respect to time, to our t variable. So, alright, the derivative of this left-hand side equals the derivative of the right-hand side. Alright, let's go ahead and just skip writing that whole thing out again. Instead, let's just go ahead and say, okay, so it would be the derivative of this first term here, 6y squared. The derivative of 6y squared will be 12y dy dt. Why is that? Because remember, from like implicit differentiation, y depends on t. This is effectively a little chain rule type thing. There's an inside part, y as it depends on t, and there's an outside part, that quantity squared. The derivative of the outside part was easy, and the derivative of the inside part is just dy dt. Alright, the second one. Oh, sorry, that equals plus. Let me use this here to clean this off. Plus, okay, our original thing was x squared. The derivative of that is 2x dx dt. Again, it's like a little chain rule. X depends on t. We know that, right? X depends on t. And so it's like an inside function and an outside part. We took the derivative of the outside part times the derivative of the inside part. Is equal to, oh boy. Derivative of 2 is nothing. Alright, I'm going to put this negative sign on the outside here. And then, alright, this inside part here, this part here is a product rule. Derivative of the first times the second plus the first times the derivative of the second. Derivative of the first will be 3x squared dx dt times the second part plus the first part times the derivative of the second part. Alright, let's see. Derivative of e to whatever is just e to that same thing times the derivative of the inside part. And the derivative of that inside part is just -4 dy dt. So doing this on a child's white dry erase board is not necessarily... I should have made more room over here. Anyway, but you have the exact equation right there on the handout here. Now, when I did this on the handout here, I kind of fixed away these signs. This is all kind of messy here. So let's go ahead and make this a little bit easier. So this is 12y dy dt plus 2x dx dt is equal to. Alright, so if I say, okay, there's going to be a -4 in front of here, but the whole thing has a negative in front of it. So it's going to be 4x cubed y e to the 4 minus 4y dy dt. All I did is just gather all the terms up over here. And then this one is minus 3x squared e to the 4 minus 4y dx dt. Did I miss anything on that? I don't think I did. Okay. Whew. This is looking a really big mess. It's a very powerful problem. We really feel like this isn't Algebra 2 anymore. We can be doing these big problems here. Alright, so what I did next is I pulled all the terms that have dy's in them to the left side of the equation, and I pushed everything that has a dx dt over to the other side of the equation. So let's do that here. Let's see. This term's got a dy dt, so let's leave it on this side. This term's got a dy dt in it, so let's pull it over to this side of the equation. That's the end of terms that have dy dt's in them, equals This term's got a dx dt, so he's got to go over here. And this term has a dx dt, he stays over here. Oops. Oh, okay. All right. All right. You could, let's see. We'll leave the right-hand side of the equation alone for right now. Let's on the left-hand side of the equation, let's just factor out that dy dt, because all the terms have that in common. And that's just equal to what we had before. All right, and then to get dy dt, let's just divide this thing in the square brackets over to the other side. Dy dt equals, what we had before will be the numerator. All over. What this term here that was in the square brackets will move down here onto the, we're going to divide it through to the other side. Okay, now that is what I have at the bottom on that, the second problem there. I have got that far here. Now here's the deal. That looks like a horrifying mess, but actually it's not that big of a deal because you have the value of, this is what you want. You want dy dx. That's what the problem is asking you to find. Here's an x. You have the value of x. Here's a dx dt. You have the value of dx dt. Here's another x. All right, here's a y. Now that looks like e to the something something over here, but actually y is equal to 1. 4 minus 4 equals 0. E to the 0 will be just 1. So this whole thing is actually, this part whole right here is not hardly horrible. dx dt, again, you have that number right here. It's negative 4. You have a y. Y is equal to 1. You have the x. It's equal to negative 2. And again, this whole term will just be a 1. It's actually not some huge mess once you actually plug numbers in. It looks terrible. It looks impressive. But when you actually plug the numbers in and crank it a little bit, it just turns out to be 8/11ths. All right. So in other words, if you could make this graph on Desmos or something, and I'm going through with Desmos withdrawal here, you make a graph of this here. At that point, the derivative of y with respect to t would be 8/11ths. Okay. And you can't actually do the dy dt part on the Desmos, but it would be a very interesting graph to have made stuff on there. All right. Whew. Well, hopefully any problems that we do like on a homework or on a test or something like that, or exit ticket or something, would not involve quite such a messy looking derivative. I actually chose this one in part because it looked messy, and it got kind of messy, but actually all kinds of things canceled out towards the end and so on. All right. How come we didn't, right at the beginning, just plug in the x and the y? You plug things in for x and y at the very end of the step. Get everything to be dy dx, or dy dt rather, or whatever it is you're solving for in that problem, and then at the very last step, plug things in. If you had plugged in numbers here, x's and y's, you just would have gotten like some constant on each side. And then you took the derivatives, you'd have 0 over 0. You wouldn't have known what to do with any of that. All right. After this, all the problems I want to show you are story problems, and so, you know, we're going to move on to the next video now, and obviously let me know if you have any questions about these problems.